Welcome friends, Igor is here, and in this video we will define two key operations on column vectors. In this lesson we will define a vector space of column vectors of fixed size, and we will define two operations, the operations of vector addition and scalar multiplication. Let's get started. Let's recall that a column vector of size n is an ordered list of m numbers which is written vertically from top to bottom. The vector space Cm is the collection of all possible column vectors of fixed size m whose entries are complex numbers. It is not an accident that we use the word space to denote this object. We will understand the meaning of this word later in the course. Let's define what it means for two vectors to be equal. If we have two vectors u and v of the same size, then they are equal if they have identical components. In other words, the component I of vector u is equal to the component I of vector v for each I from 1 to m. Let's use our new definition of vector equality to come up with an efficient way of writing linear systems. Suppose we have a linear system with three equations, and in our usual general notation, writing this linear system requires using three equalities. But now we can replace three equalities of numbers with one single equality of column vectors. Let's define the operation of column vector addition. Suppose we have two vectors u and v of the same size. Then the sum of the vectors u and v is defined as a new vector denoted by u plus v, which has the following property. Component number I of this new vector is component I of the vector u plus component I of the vector v. In other words, we add two vectors component-wise. This is a binary operation in the sense that as an input it takes two column vectors of the same size, and as an output it produces a new vector of the same size as the two original vectors. I must confess that mathematicians are not rich. It's difficult for us to get funding for our research, and therefore we cannot afford to buy too many new symbols. Because of this, we often have to reuse the symbols we already have, and this is exactly what's happening in this definition. The plus symbol serves double duty. The plus sign on the right-hand side is the old known operation of the addition of numbers, because it tells you to add components of column vectors and the components are numbers. But the plus sign on the left-hand side corresponds to the new operation, the operation we just defined. It is the operation of the addition of vectors. So, if you see a plus sign, how do you know if it's an old operation, the addition of numbers, or if it's a new operation, the addition of vectors? Well, look what's around the plus sign. If the plus sign stands between two numbers, it means it's an addition of numbers, and if a plus sign stands between two vectors, it means this is the operation of the addition of vectors. Let's look at an example how to add column vectors. We have two vectors u and v of size 5, and to add them up, we simply add the corresponding components of the two vectors. As you see, this is a fairly straightforward and simple operation to perform. The second operation we are going to define in this video is the operation of scalar multiplication of column vectors. Suppose we have a column vector u of size m and a scalar alpha. By scalar we usually mean a number. Then the scalar multiple of the vector u by the scalar alpha is a new column vector, which we denote by alpha u, which has the same size as the original vector, and it is defined as follows. We simply scale every single component of the original vector by the same number alpha. In fact, mathematicians are so poor that we can't even afford any symbol whatsoever for this operation, so we simply juxtapose the two symbols. And the convention for this is very strict. First comes the scalar, second comes the vector. This operation is somewhat different from the operation of vector addition in the following sense. In this case, We still combine two objects, but they are different objects. We combine a number with a vector, and the result of this operation is a new vector of the same size as the original vector. Here's an example of a scalar multiplication operation. We have a vector u of size 5, and let's say we take 6 for the scalar alpha. Then we scale our vector by the scalar 6. This means we multiply every single component by 6. Again, as you see, this is a very straightforward and simple operation to perform. If you found this video useful, please like it to help others discover this content, and subscribe to the channel to see more of these videos. In the next video in this series, we will discuss properties of these two vector operations. I will see you later.